I'm going to continue my discussion of geometric optics. At the very end, I misspoke on one equation because I was moving so fast, and I want to correct that, but I also want to remind you what was underlying where I was going, and then I'm going to do some applications. So we're looking at the propagation of gravitational waves through the real universe, where it is curved. It's curved by the curvature of the universe as a whole. It's curved because of the presence of galaxies and stars and black holes and so forth. And so just ignoring the stars and galaxies, I just drew a picture of the universe as though it were a closed universe. This would be an embedding diagram for those who know about it for a closed Friedman universe. And we imagine gravitational waves that are propagating through this universe with phase fronts that are gently curved. The source was somewhere down here, and with a reduced wavelength, lambda bar. This is the radius of curvature, at least of the spatial sections of the universe. Lambda bar is very small compared to the radius of curvature of the background space-time, and I'm also requiring that lambda bar be small compared to the radius of curvature of the phase fronts. And so in the embedding space, you could go out and just see what is the radius of curvature of this phase front, L. I want to be small compared to both of those. And in order to get an approximate solution to the gauge condition in Lorentz gauge, so I'm going to work with the metric perturbation, Lorentz gauge, H bar alpha, well, let me write H bar alpha beta slash beta equals 0, where the slash means gradient or covariant derivative, or in this case divergence, with respect to the metric of the background space-time. And to the Einstein field equations, which in this case, in vacuum, just reduced to the wave equation, H bar alpha beta slash mu equals 0. In order to get an approximate solution, I made what is called the iconal approximation, or the geometric optics approximation. So I wrote H bar alpha beta as some slowly varying amplitude. This varies on the scale L or R, whichever is shorter. I'm just going to not want to keep writing L or R. I'm just going to subsume. I'll let L represent the smaller of L and R. L is usually smaller than R. It would be rare you would have the radius of curvature of the phase fronts. Well, no, not necessarily. I take it back. So it varies on the scale L, which might be L or R, the smaller of those two. And then we have e to the I times the phase, and the phase varies on the scale lambda bar, which is very short compared to the scale on which A varies. And I remind you that in a local Lorentz frame, the phase is just equal to omega, the angular frequency, times z minus t if the wave is propagating in the z direction, and if it's monochromatic. And if it's not monochromatic, it's just you have some sort of superposition of waves that have those kinds of behaviors. Okay. And so just as over here, if I take the gradient of phi, as I argued yesterday, you just get the wave vector, that is k up 0 is the frequency, k up z is the spatial part of the wave vector, which is 1 over lambda bar, which is the same as the frequency, since I'm setting the speed of light equal to 1. That means over here, because that's phi comma mu, because in a frame-independent language or in any kind of basis you wish, phi comma mu is still the gradient of phi. That's the components of the gradient of phi. It must be that I should define the wave vector as being equal to the gradient of the phase factor. And then it's an important point that the wave vector, like A, varies on this long length scale. The only thing that varies on a very rapid length scale is phi, the phase, and everything else varies slowly. That is, the wave vector will change as a result of gravitational redshifts, for example, and things like that, or as a result of rays bending due to gravitational deflection by the sun. But the length scales on which those changes occur are very long compared to the reduced wavelength itself. So the only thing that varies rapidly is phi. And so when we put this back into the gauge condition, as I argued yesterday, this just gives us the statement that the gravitational wave field, A alpha beta, is orthogonal to the wave vector. And when we put this into, so that when we put it into the gauge condition, that's what you get. When you put it into the wave equation, you then look at the leading order term in the power series expansion in reduced wavelength divided by the length scale L. So you look at the leading order term in this small quantity lambda bar over L. And that gives you the fact that K is null. And then you take the gradient of this relationship, as I did yesterday, and that gives you the fact that K is parallel propagated along itself. So that tells you that there exist curves which are null geodesics. In space-time that are called the rays, and the wave vector K is the tangent vector to a ray. Okay. And so, as one sees then, when one looks at the next order term, in this ratio, one finds the equation which I wrote down wrong on Monday, which says that A alpha beta slash mu K mu is not equal to 0, but rather it's equal to minus 1/2 K mu slash mu times A alpha beta. And so this is a propagation law, which I can write equally well in geometric frame-independent language as the derivative along K of A tensor. That's what's going on here, is you're taking a derivative along K. That's minus 1/2 the divergence of K times A. So that's just the same equation in frame-independent language. What this says is then that A is transported along the null rays according to a law that has it changing in some manner that's governed by the divergence of K. This is a transport law for the gravitational wave field, or the amplitude of the gravitational wave field, a transport law for that field along the rays. Okay. So I'm going to want to understand in simple terms what are the simple physical meanings of these statements. Well, let me begin with the issue of the rays, okay? So we all know that if you go to a local Lorentz frame and you have some sort of wave, and it has some wave vector k, or some frequency omega, and some spatial part of the wave vector k, that wave then can be described quantum mechanically in terms of quanta that are carried by the wave, or that the wave carries. And in quantum mechanical language, we know that when you quantize this wave, that you have an energy for the quanta that's equal to h bar omega, and you have a momentum for the quanta that is equal to h bar k. And so in 4-vector language, you have a 4 momentum for the quanta that is h bar times the 4-dimensional space-time wave vector. That's the 4 momentum of a quantum. And that's just from elementary quantum mechanics, a universal phenomenon for any kind of a wave that you deal with in elementary quantum mechanics. In this case, the waves are gravitational waves, and so this must be the 4 momentum of a graviton. When you quantize these gravitational waves, you'll get gravitons, and this will be the 4 momentum of the graviton. And the laws of geometric optics have told us, since the graviton's 4 momentum and the wave vector only differ by a constant, they tell us that the derivative of p along p is equal to 0. They also tell us that p squared is equal to 0. What that says in words is that the graviton moves at the speed of light. Why? Because its 4 momentum is null, just like the 4 momentum of a photon. And it moves along the geodesic, just like a photon. So in other words, it moves along a null geodesic through space-time. And so that comes out from just looking at the geometric optics or iconal approximation for the classical gravitational waves. Now, it turns out that when you're doing classical physics, it is very frequently the case that many things in classical physics become much easier to understand and to think about and to quickly figure out what's going on if you use quantum mechanical language, even though you may be very far into the classical domain, even though the truly quantum mechanical phenomena, the non-classical phenomena, are very small. Still, classical physics is a consequence of quantum physics. It's an approximation to quantum physics. And so the fundamental underlying quantum theory often gives you ways to think about the classical physics that, in fact, because the classical physics is an approximation, it gives you ways that, in fact, turn out often to really be very powerful and useful. And so in this case, where there is no hope in your great-grandchildren's lifetimes to see any quantum mechanical effects associated with gravitons, nevertheless, there's a lot of power in thinking about gravitational waves in the language of gravitons. And we're going to see this more a little bit later on. The fact that the gravitons obey the same laws of motion and having a null 4 momentum as a photon means that all of the phenomena that you would see for the behavior of photons in curved space-time, you also see for gravitons. And in particular, you will see gravitational redshifts and cosmological redshifts for gravitons. And similarly then, since the graviton energy is just h bar times its frequency, you'll also see gravitational redshifts and cosmological redshifts for frequencies. And I will give you exercises to work that out in specific, simple, and important astrophysical cases for gravitational waves that are climbing out of the gravitational field of a black hole, and they're propagating through a Friedmann cosmological model. So that'll be on the exercises for you this weekend. Let's go to the propagation law that we get out of geometric optics. That propagation law looks a little bit peculiar with this divergence of k on the right-hand side, but I will tell you, if you do precisely the same thing for the electromagnetic field, and you're working with the vector potential of the electromagnetic field instead of with the gravitational wave metric perturbation or trace reverse metric perturbation. In the electromagnetic case, you will get out precisely the same equation, although the A here will be a vector potential, or the amplitude of the vector potential, having factored out the rapidly oscillating phase. And so, again, the analogy between the electromagnetic case and the gravitational case is extremely tight. The same physics will come out. So I want to actually talk a little bit mathematically about what does come out from this mathematics. And for that purpose, I want to take the amplitude of the gravitational wave, A alpha beta, and I want to expand it over the gravitational wave fields H plus E plus alpha beta plus H cross E cross alpha beta, where then in a local Lorentz frame near the source, so we have our source over here. It's emitting gravitational waves. They're traveling out through the universe. I go in here near the source and I build myself a local Lorentz frame. And in that local Lorentz frame, I make some choice in the transverse directions as to which axes I use for to project onto to get the plus and cross polarizations. That is, I make a choice of what is the x-axis in here, what's the y-axis. The waves are propagating in the z direction. I will normally choose the x-axis to be along the theta direction of the spherical polar coordinate system, and the y-axis to be along the phi direction. That's a natural choice. And the z-axis is along the radial direction. So that's the usual choice. But I make some choice. And having made that choice, then in that local Lorentz frame, E plus is defined to have E plus xx is equal to minus E plus yy is equal to 1, and E plus xy equal E plus yx is equal to 0. In other words, this just carries the directionality associated with the gravitational wave amplitude. It guarantees that H plus E plus alpha beta is something that has components, the xx component. Oh, let me start over here. So that guarantees that H plus E plus xx is equal to H plus. That's the AXX for the plus polarization. And the AYY for the plus polarization is just equal to H cross. Is equal to minus H plus. It's equal to H plus EYY plus. But EYY plus is minus 1, whereas EXX plus was plus 1, so that's just equal to minus H plus. So this is just a fancy way of getting out the usual definition of what H plus and H cross are. But a way to do it so that I have everything now in tensor language. Similarly, for the H cross. For E cross alpha beta. Okay. So having done that, then I can look at my propagation law, the derivative along K of A alpha beta. Well, let me write it, of A thought of as a tensor, is equal to the derivative along K of H plus E plus, the tensor E plus H cross the tensor E cross. And so this derivative is going to have to differentiate the H and the E in both cases. Well, it's straightforward to do just a little bit of the mathematics and see that the consequence of this is that one way to satisfy this, the natural way to satisfy this, is to take the derivative along K of E plus vanishes, as does the derivative along K of E cross. So that's a transport law. I gave initial conditions for what E plus and E cross were in this local Lorentz frame. Now I have a transport law along a null geodesic going out of here. And this transport law just says that you're supposed to parallel transport these E's along the null geodesic. Okay. These E's are called polarization tensors. Okay, so let me put that up here. So the E, let me call it EJ alpha beta, is the polarization tensor for the plus polarization. Or, I'm sorry, for the J polarization, where J can be plus or cross. Okay. Yeah.
Just looking at these components of plus and cross polarization tensors, we see similarly for E cross. What are they?
So what I mean by that is that E cross XY is E cross YX is 1. And the others vanish. No, because we know that that the gravitational wave field has to be symmetric in the two slots, and this is the symmetry in the two slots. Okay.
Right, and so over there when you wrote AXX plus on the left-hand side of the board, you don't really need that plus.
Where?
It's the current board.
Yeah.
Yeah, right there. AXX plus. Yeah, right there. To the left.
Yeah.
That thing. You don't really need the plus there or something.
That's also true. AXX will be that.
Right,
that's right. Because the cross polarization doesn't contribute at all.
Right. So
absolutely.
AXX is equal. We want that to be.
AXX is equal to H plus. AYY is minus H plus.
So we choose the tensor components basically to satisfy those.
That's right. Equations. And so similarly, AXY is AYX is equal to H cross by virtue of what I've written down. Yeah.
So it's a very convenient way of...
It's a convenient way to take what we've done in elementary language and recast it in tensor language so we can then do propagational laws with tensors. Okay. Thanks for slowing me down. I mean, this is also obvious to me because I've been doing this for 30 years or so, and I forget that you have not been doing this for 30 years. Okay. Okay, so I have given polarization tensors in the local Lorentz frame, and I now have a propagation law for these polarization tensors, which says parallel propagate EJ alpha beta along the gravitational ray, for the waves ray. Okay. Well, if that's the rule for how the E's are propagated, then if I go back to my propagation equation for the gravitational wave amplitude, I see that H plus and H cross must be the guys that take care of this term involving the divergence of K. That is, I feed this ansatz, or this form for the gravitational wave amplitude back into this propagation law for the gravitational wave amplitude. And when I do that, then I get out the statement that the derivative along K of A plus is equal to minus 1/2 the divergence of K times A plus. And similarly for A cross, so let me write it AJ, where J can be plus or cross. So that's the propagation law for the gravitational wave. This should not be A's, these should be H's. I'm sorry. Okay. So to repeat, I have taken this formula. Pardon?
I'm confused. I mean, H is just a number.
HJ is a gravitational wave field. And so the full gravitational wave field is this times e to the I times the phase. Okay.
So, this is something that, that might be it's potentially confusing. The indices and the pluses and crosses are stochastically jumping.
They're stochastically jumping around depending on where I chose to put the alphas and betas. The alphas and betas, think of this as slot naming index notation. I can put this alpha and beta wherever I wish, up or down. Then I'm forced to put those alpha betas where I put the ones on the left. And then I choose to put the pluses and crosses somewhere where they don't get in the way.
So now I haven't been doing this very long. I mean, I've been doing this long enough that I see that happening, but for the people that this has never
No, that's good. That's good. That's good. Okay, and to reiterate then, so let me reiterate that we have a propagation law for the polarization tensors. Let's call that equation number 1 along the ray. We also have the ray equations. So let's go back here. We have the ray equations. Let me number these, the fundamental equations here. First of all, we have the relationship between k and phi. So let me call that equation number 1. Well, equation number 1, way back up here. Equation number 1 is the gravitational wave field in terms of its amplitude and its phase. Equation number 2 says how do you get the wave vector from the phase, the rapidly varying phase. Equations number 3 and 4, I'm sorry, equation number 3 says that the field or the amplitude is transverse, orthogonal to k, and that's a consequence of the fact that everything is being done in Lorentz gauge. Equation number 4 and 5 say that there exist rays which are null geodesics, and we're going to propagate the gravitational waves along those rays. Equation number 6 was or this equation down here was a propagation law for the gravitational wave field, but I find it useful or the gravitational wave amplitude, I find it useful to split the gravitational wave amplitude into plus and cross polarizations using polarization tensors. So that's equation number 6, where the polarization tensors have the forms that I talked about. And then the propagation law has 2 pieces. Equation number 7 here, which says that you parallel propagate the polarization tensors along the ray. The equation number 8 is a propagation law for the gravitational wave fields H plus and H cross. So that's sort of a summary of what we have. And of course, these are the guys that we are really interested in. This is the thing that LIGO and LISA is going to measure. These are the gravitational wave amplitudes, actually. I should really have, these are the amplitudes. It's actually, since I have factored out the phase e to the I phi, so let me go back in here and put that phase back in, e to the I phi.
So what are the issues now? I'm confused.
Okay, just a moment, just a moment. Or let me, I've screwed up the notation just a little bit because I factored out the e to the I phi from the beginning, and then when I expanded this guy, I used the notation for the full gravitational wave field, but in fact the full gravitational wave field is this times e to the I phi. Okay.
You also have the trace reverse.
And I'm working with a trace reverse metric perturbation, but I've made this thing traceless, so it doesn't matter. But this step, I made it traceless. And the trace satisfies the wave equation by itself, and so the trace is going to remain 0 if I set it 0 to begin with. So it's already traceless. So the fact that I'm using a trace reverse metric perturbation versus the metric perturbation doesn't matter. Okay? Now, so what I derived was the parallel transport law, or I'm sorry, a transport law for h along k, but the phase is constant along k. And so I can put the e to the I phi in here if I wish. Why is the phase constant along k? Just remember, in a local Lorentz frame, a surface of constant phase is a surface of constant omega times z minus t. But because it's z minus t, that's something that is constant moving with the wave. So the phase is really constant moving with a wave. And if you draw the surfaces of constant phase, say in the zt plane, the surface of constant phase looks like that. And the gradient of phi, which is the wave vector, the gradient of phi is something that actually lies in the surface of constant phase. And so if you've never seen this before, it's something you should go off and think about. If you have a field where the surfaces of constant phi are null, then the gradient lies in the surface of constant phi. And I'll let you go, if this is startling to you, I'll let you go think about it by yourself. Okay, some people look a little, some people look a little puzzled. So if you have a function whose surfaces of constant value of psi look like this, then the gradient looks like that. If you have one, if you now boost to a reference frame that is moving at high speed, then in the new reference frame, the surfaces of constant phase will look like that, and their gradient will look like this. It's a behavior under a Lorentz transformation. And as you boost to higher and higher velocity, so this surface becomes null, the gradient becomes parallel to the surfaces of constant value of my function. Okay.
So it's only because you're moving at the speed of light?
It's because you're moving at the speed of light, yeah. Okay, so phi is constant along the rays. A little strange. You move along the direction of the gradient of phi, and phi remains constant.
You're moving with the wave.
You're moving with the wave. Okay, so the direction of the gradient of phi is the direction along which phi is a constant. And so I derived that the amplitude, which I called h, was transported according to this law. Since phi is constant along k, I can pull the e to the I phi in here. And this quantity that I have in here now is the usual gravitational wave field, hj. i.e. h plus or h cross. The statement is that the usual gravitational wave field is transported along the rays according to this transport law.
The minus sign go over.
And there's a minus sign on the right-hand side, which I lost from over here. Okay, so I'm sorry about having screwed up the notation. I'm going to go in here and I'm going to call this hj e to the I phi now my hj. I'm going to reabsorb the phase factor, the oscillating phase factor, back into this field. And I want to rewrite this law then by multiplying by hj itself. I can rewrite this rather easily as the derivative along k of hj squared is equal to minus the divergence of k times hj squared. It's the factor of 2 that comes from this derivative that becomes the 1/2 up here. Okay. So that's just equivalent. Okay. But now I can pull this to the left-hand side and rewrite that as let me write that's equal to the gradient of hj squared dotted into k. And so if I just pull the right-hand side to the left-hand side and combine terms, I wind up with the divergence of hj squared times k is equal to 0. And this is the form of the propagation law that I really want to use. And so that says that from the gravitational wave field for the plus polarization or for the cross polarization, you can build a quantity that is divergence-free in space-time. In a local Lorentz frame, what this says is that d by dt of hj squared times k0 plus the spatial divergence of hj squared times the spatial part of k vanishes. And you recognize this as the same conservation law as you have for electric charge in electromagnetism. So that's like charge conservation. This is the 4-vector form. This is the 3 plus 1. That is when you split up into space and time. Well, it seems reasonable to expect then that this conserved quantity, this the analog of conserved charge, is going to be graviton number. I mean, what else could be conserved here? If you have something that is conserved in the sense of the charge is conserved, you just don't have anything else around it could be except graviton number. Clearly, gravitons are being conserved if these waves are propagating freely through space-time. There's no place for them to go. If it's propagating through matter, they might be slightly absorbed or scattered or something, but propagating freely through space-time, they ought to be conserved. And so we have a guess that the number flux 4 vector for gravitons of type J, that is plus polarization gravitons or cross polarization gravitons. So let's call that the number flux 4 vector. It's like the charge current 4 vector. It's a thing such that the time component would be the this number flux 4 vector for gravitons. It's a thing such that the time component would be the number density of gravitons in any reference frame. The number per unit volume of gravitons that would be seen by an observer who can just sit there and count gravitons. Now, as I said, we're not going to be able to do this in your grandchildren's lifetimes. But nevertheless, to think about it in this language has a lot of power. And N and J, the spatial part, would be the flux of gravitons in whatever reference frame I'm doing this decomposition into temporal part and spatial part. That is, the number of gravitons crossing a unit area per unit time, where the unit area is chosen to be perpendicular, well, okay, crossing unit area per unit time, where the unit area is in the direction that's orthogonal to this. That is, the gravitons are moving in this direction, so we pick the area to be orthogonal to the direction in which the flux of gravitons is propagating. And so our guess then is that this number flux 4 vector for gravitons is just equal to or proportional to hj squared times k mu. I'm going to prove that that's the case a little bit later today. Okay. So that's one version, or one way to think about this propagation law. Another way to think about it is in terms of radii of curvature of phase fronts as seen in a local Lorentz frame. So if I have my waves propagating through a local Lorentz frame, and I look at in the phase fronts, and so the waves are propagating like this. This is a spatial diagram. Then these phase fronts have some radius of curvature. It's really an average of the radius of curvature in this direction and that direction, but it's the usual radius of curvature that you would define for a surface. Let's call R the radius of curvature. Now, typically, if you try to draw the curve, the radius that goes back until these normals converge, you'll get out of the local Lorentz frame. That doesn't matter because radius of curvature is really defined by just looking at the shape of this surface. Okay, so it is a local concept. So I claim, and the mathematics is in reading that I will give you, I claim that what this equation says, this propagation law says, is simply that as you look at any local Lorentz frame, Hj will be changing as you go along through the local Lorentz frame as 1 over the radius of curvature of the phase fronts. As it dies out as 1 over r, but r has a very special and precise local meaning. It's the radius of curvature of the phase fronts, as seen in some local Lorentz frame. It's quite natural that that would be the meaning of this, because if we're talking about conservation of gravitons, it would be like conservation of photons. And in order to conserve photons, you should have better have the amplitude of your field die out as 1 over r to conserve photons. And similarly, to conserve gravitons, the amplitude of the field should die out as 1 over r. So that's the second way to think about this. There's a third way to think about it that's also powerful. These ways are all equivalent. This third way says, let's look at a bundle of rays. And so this bundle of rays corresponds, if the wave is propagating in the z direction like this, at a particular moment of time, the bundle of rays, as seen in our reference frame, we just see that bundle of rays as a bunch of gravitons, because the rays are the world lines of the gravitons, a bunch of gravitons that are sitting here side by side and are propagating in the z direction. So the cross-section, the intersection of our reference frame with this bundle of rays is just a two-dimensional set of gravitons that are sitting here in a surface of constant phase in our reference frame. And we can look at those, that set of gravitons, and we can ask, what is the surface area of this bundle of gravitons that are propagating along at the speed of light, and they're all sitting here side by side in a plane orthogonal to the propagation direction. So I want to talk about the cross-sectional area of this bundle of gravitons. Now let me draw a space-time diagram to illustrate what is meant by this bundle of diagrams from a space-time viewpoint. In our reference frame, so this is in then our local Lorentz frame, here's the t direction, here's the z direction in which the waves are propagating, and here is the x direction, and I'm going to suppress the y direction. Okay. And I want to draw this diagram a little bit carefully. The bundle of rays that I'm talking about is a bundle that all lies in a surface of constant phase. So let me draw a surface of constant phase. These waves are propagating in the z direction, so a surface of constant phase looks like this. Looks like that. That's a null. Well, this is supposed to be the null direction. Looks like that. But then it comes down here. Looks like that. So, and the individual rays in here, here's one of the rays. It's just moving along at the speed of light. Here's another ray. So there are a set of rays that are the world lines of the gravitons that I was talking about. They all lie in the same surface of constant phase. Phi equal constant equal omega times z minus t. So that's the same thing as z minus t equal constant, which is the surface I've drawn. Now, when we look at this at a particular moment of time, what we see is this horizontal piece going right through here. I think I have some brown chalk. So here's the slice that we see at a particular moment of time. That's a one-dimensional slice. I subtract the y direction. The y direction will give me the second dimension. And that will give me then snapshots of all the gravitons that are traveling along these rays that are inside this piece along the x direction and a similar piece along the y direction. So it's a little square or rectangle sitting here, orthogonal to the z direction as seen by us. Okay. And so we can then just ask ourselves, what is the cross-sectional area of this set of gravitons? Or equivalently, of the bundle of rays that I've chosen. So that's asking, what is this length times the corresponding length in the y direction? And that gives me a cross-sectional area. So just in the elementary sense, what's the cross-sectional area that is subtended by a bunch of gravitons in the plane orthogonal to the direction they're propagating? If you just look at them, and we're going to color all these gravitons green, and we're going to then just follow these gravitons. Okay. So I want to make a key statement, and that is that this cross-sectional area is independent of the reference frame in which we measure it. Why is it independent of the reference frame in which we measure it? Well, suppose we made a boost to a reference frame that's moving not in the z direction, but in the x direction with respect to this one. If we're in a reference frame moving in the x direction, then a slice of constant time in this new reference frame will be a slice that is tilted up like that. So that's in the new frame. That's the slice of constant time. And so what I claim is that the length of this line, which is the length along one edge of my bundle of gravitons, is the same as the length of that line, viewed as lines in space-time. I'm going to give you a very simple proof. Okay? And so I'm going to introduce a vector that points along this line from the origin, and I'm going to call that C. It's a 4 vector, but it's purely spatial as seen in the original reference frame. And similarly, there's a purely spatial vector C prime as seen in the other reference frame. And my claim is that the length of C and the length of C prime are the same. And the way to prove this is to look at the difference between C prime and C. That's this vector here, which is just some multiple of the wave vector because it's pointing along a ray. So the statement is that C prime is equal to C plus some multiple of K. So C prime squared is just C squared plus 2 alpha C dot K plus alpha squared times K squared. K is null, and so K squared vanishes. C points in the x direction, but K lies in the ZT plane. And so Xi is obviously orthogonal to K. And so Xi dot K is 0. And so that says that Xi prime squared is the same as Xi squared, so they have the same length. And just turning that into a two-dimensional statement, then the cross-sectional area of the gravitons is seen by you and me in our reference frame, where we're looking at the same set of gravitons that we've colored green. And it's seen by somebody moving in an arbitrary direction at an arbitrary speed with respect to us. The cross-sectional area will be the same. Now let me just remark that in the theory of black holes, the horizon of a black hole is a null surface, just like this surface of constant phase. And this same argument is used in the theory of black holes to show that the cross-sectional area of the horizon, the two-dimensional surface area of a horizon, is independent of how you move. If you're falling through the horizon and you measure its surface area, you'll get the same surface area however you fall through the horizon. Okay.